Hello and welcome back. In the previous video, we've discussed how you can calculate the current that flows through and the voltage drop across different circuit elements. In this video, I want to discuss how we measure these quantities in real life. And the first thing I want to talk about is something called an ammeter, which probably should be really called an amp meter since it measures the current that flows through something. And what an ammeter does is it measures the current that flows through the ammeter. So in order to measure the current that flows through a circuit, you have to connect the ammeter in series with the circuit, so that all of the current that flows through your circuit first flows through the ammeter. And if we step back and think about this, you realize that when you connect an ammeter to a circuit, you're actually modifying the circuit, because now all of the current has to flow through the ammeter before it goes through the rest of your circuit. And ideally, what we want to do is we want to design the ammeter so that when we connect the ammeter to the circuit, it has very little impact on the current that's flowing through it. That way, the current that we measure is the same as the current that you get when the ammeter is not there. So the way we do this is that, if you think about this, if the ammeter had a very large resistance, then connecting the ammeter to your circuit would decrease the amount of current that's flowing through the circuit. However, if you design the ammeter so that it has very little resistance, connecting the ammeter to your circuit has almost no effect. So we always try to design an ammeter so that it has very little resistance. And actually, ammeters are relatively simple things. We can easily understand how they work. We haven't really talked about this yet. We'll talk about it a little bit later in the year, but it turns out that when current flows through a loop, it actually creates a magnetic field that kind of looks like this. And it turns out that the strength of this magnetic field is related to the current that's flowing through the loop. So the way you build an ammeter is you take a block like this with a needle attached to it, and then you run a whole bunch of current through a coil that goes through this block here. And the idea is that the current that's flowing through this coil is going to generate a magnetic field. And the strength of this magnetic field is related to the current flowing through the coil. And then you place this thing between two ends of a magnet. So you got the north end here and the south end here. And these magnets will exert a force on this coil. So the magnetic fields created by the magnets will interact with the magnetic fields created by the coil. And that'll exert a force on the needle that will deflect the needle. And the amount that the needle deflects by will be related to the current that's flowing through the coil. And this type of device here is called a galvanometer. And actually, if you look at the old-fashioned types of ammeters, and kind of try to draw a picture of what they look like, they usually have this little dial over here on the top, and there will be a needle that will point to different numbers, and they usually range between 0% on one side and 100% on the other. And then there's usually a little dial in the center, and you could have something like a 1 amp scale, or 100 milliamps, or 10 milliamps, or 1 milliamp. And what you do is you point the scale to one of these things. So for example, if I point the knob so it points at the 10 milliamp scale, then what that means is that this 100% reading over here corresponds to 10 milliamps. So if the needle points at something like 25%, then that means the current that the ammeter is reading is equal to 2.5 milliamps, or 25% of 10 milliamps. And the way that you actually design an ammeter so that it has different scales like this is that you take your galvanometer, which I'm just going to denote with a circle with an A in it since it's something that measures amps, and you actually place it in parallel with a resistor. So the idea is that you have current that's flowing in here and the current that's flowing out here, and you're trying to measure this current. Now, if you had something like 1 amp flowing through here, that's a very large current. If you had 1 amp of current flowing through this coil in your galvanometer, it would exert a very large force on the needle. And what would happen is that needle would just deflect all the way to 100%. And that's not very useful, right? We want to actually be able to measure that current. So what you do is you put the galvanometer in parallel with an extremely small resistance, so that most of that 1 amp will flow through this shunt resistor down here, and only a little bit of the current will flow through your galvanometer. That way your galvanometer will give you a reading other than 100%. And this is actually how you design an ammeter so that it'll have different scales, is that you have to design the ammeter so that it has just the right resistances down here, so that 100% corresponds to 1 amp when it's in a 1 amp scale. So actually what you're doing, Oh, I just shut down that picture. But what you're actually doing when you change that knob down there is you're actually just changing that resistance that's in parallel with the galvanometer. And a really interesting thing is that it turns out that if you have a device which can measure current, you can use that same device to measure voltage. So that's why if you go to a place that sells testing equipment like Radio Shack or something like that, you'll notice that all of the amp meters also measure voltage. And the basic idea behind this is that if you place a known resistor in series with an ammeter, then by measuring that current that flows through this resistor, you can determine the voltage that was applied across the resistor, since the current that flows through a resistor is equal to the voltage across the resistor divided by its resistance. So that current that flows through the resistor is directly related to the voltage across the resistor. Now, because we use a voltmeter to measure the voltage difference between 2 points in a circuit, you always hook up a voltmeter in parallel with the circuit. So for example here, if I want to measure the voltage difference between this point and this point, I hook up one end of the voltmeter to this point and the other end of the voltmeter up to this point over here. Now once again, when I hook up this voltmeter to the circuit, I'm actually changing the circuit, because now the current could either flow through this resistor or the current could flow through the voltmeter. And remember, we always want to design our measuring device so that it has very little impact on what the circuit is doing. So in this case, I want to design the voltmeter so very, very little current will actually flow through the voltmeter. And the way we do this is that we choose that resistor that we're going to put in series with the ammeter so that it's very, very large. That way, very little current flows through the voltmeter. Most of the current will flow through the resistor. And the last thing that I should talk about, I don't think I have a slide for this. It turns out that you can also use an ammeter to measure resistance. And the way that we do this is that basically you place a known voltage source in series with an ammeter. So you take something like a battery and you hook it up to an ammeter. And then now if I hook up a resistor between these two ends, so let's say I want to measure some unknown resistor. I've got a resistor I found laying around and I want to measure what it is. Well, if I hook up that resistor to this thing, by measuring the current that flows through this resistor, I can calculate what that resistance is. So remember that the current that flows through a resistor is equal to the voltage across it divided by the resistance. And since I know the voltage I'm applying, because it's like maybe a 9-volt battery or something like that, by measuring that current that flows through the resistor, I can determine what its resistance was. Now, one interesting thing to point out about this is that the current is inversely proportional to the resistance. And what this means is, remember I said that if you look at these old-fashioned ammeters, they have this dial over here, and on the right side it corresponds to like the maximum current, and on the left side it corresponds to zero current. And if we think about this now, if I have something that's like let's say like a 0 ohm resistor, well then there's going to be a whole lot of current that's going to flow through the circuit because it basically has no resistance. So at 0 ohms, I'm going to get a maximum current reading. So if you look at these old-fashioned scales, this right side that normally corresponds to a maximum current, that actually corresponds to 0 ohms when you're measuring resistance. And on this other side, so if I had like a really, really large resistor here, well then basically no current's going to flow through this circuit. So we get 0 amps current when we have a very large resistance. So this side over here is going to correspond to like an infinite resistance between the two ends. And then these tick marks between these two sides for resistance are really nonlinear. So over here they're real far spaced apart, and then they get real bunched up over here. And this is because the current is inversely proportional to the resistance instead of directly proportional. So you get this really kind of nonlinear scale. And I think this is a pretty good place to end this video. And the next video, we're going to talk about how you can calculate the equivalent capacitance.